Everyone, welcome back to my YouTube channel. So for this class we'll be looking at partial fractions. So if I was to give you a problem of this nature, let's say 5 over x minus 1, add this with 1 over x plus 2. The final solution for this will be 6x plus 9 over x minus 1 and x plus 2. So this is the normal addition of, just if you have fractions, when you add them, this is the final solution. But with partial fraction, it's like we'll be doing the reverse of this method. We'll be coming from this point going to this point, and that is what we call partial fraction decomposition. So to understand this topic well, we're going to look at 4 cases in which we can do partial fraction decomposition. Okay, so the first case we look at is what we call the non-repeated linear factors. So this kind of an expression is where for each non-repeated linear factor of the denominator, so the procedure for finding a partial fraction decomposition of a rational expression, it always depends on the factorization of the denominator of that rational expression. So the first case we're looking at is what we call the non-repeated linear factors. So in this case, you find that the denominator is non-repeated. Just for instance, if I was to say this is an expression, if we have 3x minus 1 over then x, 3x plus 4, and then x minus 2. So if you look at this expression, let me just write it properly. So if this is our expression, so looking at the denominator, there is no factor that is repeating here. There is nothing that is squared on the denominator. So the partial decomposition will be of the form a over the first factor, which is x, then plus b over the other one, which is 3x plus 4, and lastly plus c over x minus 2. So this will be the partial fraction decomposition of a case where it's non-repeated. So let's look at an example. So here we have the example: find the partial fraction decomposition of x plus 11 then over that quadratic. So when you are given such an expression, first look at the denominator. So this is a quadratic expression. Is it reducible? So we can try to reduce it either by using the product sum or the quadratic formula, but the product sum would be better so that at least we group the terms. So in answering this, let's solve it. First, let's try to reduce the denominator. So the denominator can be reduced to, let me write it here. If we were to factor it, we would have these two factors, which is x plus 3, and then we'd also have x minus 5. So if the denominator is reducible like that, we should reduce it. Then we write this expression. So that means we're having x plus 11 over, so we're changing the denominator to x plus 3 and x minus 5. So now when you look at this expression that we have, this is a non-repeated linear factor. There is no part of the denominator that is repeating again. So that means our decomposition will just be straightforward. We'll have a over x plus 3 and we'll have b over x minus 5, like that. So to now solve this, we'll multiply both sides of the equation by the least common denominator. So the least common denominator is x plus 3, x minus 5. If we were to multiply this throughout this expression, would have, so what I'm talking about is we're saying we multiply with this, like x minus 5. We multiply this for the whole expression of yes, so we multiply x plus 3 and x minus 5 throughout this whole expression. So you agree with me that when we multiply for the first part, the x plus 3, x minus 5 will cancel out. We'll be left with x plus 11 for the numerator is equal to, on this other side, if we multiply x plus 3, x minus 5 with this, the x plus 3 will divide, will remain with a, x minus 5. And on the other side, we'll also remain with b, x plus 3, like that. So I'm only showing for this part. For the other parts, I won't be showing, since we already know from this example. So from here, we can expand the expressions that we have. So we're having, so we have ax minus negative 5a plus bx plus 3b. Then we can collect like terms on the right hand side. Variables with x, we're having a plus b with x, then plus, we're having, okay, let's start with the one with a. So we're having negative 5a plus 3b as the other expression. So looking at these two expressions, we're going to use what we call the definition of equality of polynomials, where we equate coefficients on the left hand side and the right hand side. So that means the coefficient of x here is a plus b. The coefficient of x here is 1. So that is, we're saying we're going to equate 1 from this side is equal to a plus b. These are coefficients, these are constants, sorry. So the constants also will align them with the constants. So that is, we're having 11 is equal to negative 5a plus 3b. So these are two systems of equations that we can resolve. So we can multiply maybe this one with 3. So at least it becomes 3. Sorry. So it becomes 3 is equal to 3a plus 3b. Then we're having 11 negative 5a plus 3b. Then we can subtract throughout. So that is negative 3 minus 11, we'll have negative 8 is equal to, then we'll have 8a, then this is 0. So a is equal to negative 1. So if we replace this value in the first expression, this one, we'll have 1 is equal to negative 1 plus b, giving us b is equal to 2. So now that we have the two values, a is equal to negative 1 and b is equal to 2, we're going to replace them in our expression here as our final conclusion. Let's do that. So now replacing, we're saying a is negative 1. So our final solution will be negative 1 over x plus 3 plus b is 2. So it will be 2 over x minus 5. And when you do this, then you're done. So this is our final solution. So don't leave your answers by just finding the value of a and find the value of b. You need to indicate how you've decomposed the expression. So the next case is what we call the repeated linear factors. So with this case, when you look at the denominator, so our focus is usually the denominator. So when you look at the denominator, we have a factor there that is repeating, and that is x minus 2. It has a square on top. So x minus 2, if it's square, it means we're having x minus 2 and we're having x minus 2 again. But when it comes to partial decomposition, it takes a different stance. So in decomposing this one, since it's a repeated factor, we're going to have the first part will have x minus 2 the way it is. Then on the next factor we'll have the repeated factor again, this time with a square. So take note of that. So first you write the expression as it is without a square, then now you include the square. Then finally we have plus c over 2x plus 1. How the decomposition is done for a repeated linear factor. Let's look at an example. So in this example, we are told to find the partial fraction decomposition of this expression. So when you look at the denominator, we have an expression with a square, and that expression is repeated. So how do we decompose it now? So our decomposition in this case will take the form, we'll have a over x, which is the first term there, then plus, so it will be b over x minus 1. Then the next one now will carry the square as well, x minus 1 square. So we've decomposed it. Now we just need to find the values of a, b, and c. So like we did previously, we'll multiply with the lowest common denominator, and that is x with x minus 1 square. So if we multiply this expression, this one, the denominator, if we multiply it throughout this whole equation that we have, we'll have x squared plus 2x plus 7. So the numerator will repeat. So is equal to, then in this case, x and x will divide. So a will multiply with x minus 1 square plus, for b will multiply with x and x minus 1. So we'll have b multiplying x minus 1 and x, plus, then c will just multiply with x. So we'll just have cx. So we can expand this expression and also expand this expression. So we'll have x squared plus 2x plus 7 is equal to, expanding this we'll have a x squared minus 2x plus 1. Then here we'll have bx squared minus bx plus cx. Then we can have a multiply through. We'll have ax squared minus 2ax plus a. Then we'll maintain this side. We're having plus bx squared minus bx plus cx. Then we can collect like terms and we factor. We'll collect like terms. So that is, we'll maintain this side. So ax squared with the bx squared, so we'll have a plus b x squared. Then we'll have the variables with x, which is negative 2ax, negative bx, and cx there. So that will be plus negative 2a minus b plus c, then x outside. Then we also have the term with which is just a constant, which is plus a. Okay, So now, using the definition of equality of polynomials, we'll equate the coefficients. So with x squared, the coefficient we have is a plus b. With x squared on the other side, the coefficient we have is 1. So we equate, so it will be 1 is equal to a plus b. The coefficient for x is this expression, and the coefficient for x here is 2. So it will be 2 is equal to negative 2a minus b plus c. Then finally, the constant a is equal to 7. So we'll have 7 is equal to a. And we can solve it from here. So since a is equal to 7, if we replace a 7 here, b will be equal to negative 6. So we'll have b equal to negative 6. And if now we replace 7 here and negative 6 here, c will be equal to 10. So now that we have the three values, we can now replace them in our partial decomposition. So our decomposition, we're now replacing, where there is a, we'll put 7. So 7 over x plus, for b, we're saying it's negative 6 over x minus 1. And finally, for c, it's 10 over x minus 1 square. And that's how you do it for a repeated linear factor. The next case we're looking at is non-repeated quadratic factor. So for like this expression I've written, if you look at the quadratic expression we have, is this one. So if you were to try to reduce this expression either by product sum method or whichever method you would think of, factorization, you find that it would be difficult to reduce this expression. It's irreducible. So it's irreducible and it's a quadratic factor. So the decomposition takes a different turn from here. So first, before you solve, you need first to try. You try to reduce the quadratic. If it fails, then now you can apply the method we're about to look at right now. So in this case, if you have an irreducible and it's non-repeated quadratic factor, the decomposition will take the form of, we're going to have ax plus b over the same quadratic expression, which is x squared plus x plus 1. Then we'll have plus c over x minus 4. So for this other factor. So take note on how we've written our decomposition for the quadratic. It takes this form. So we'll have ax plus b, then over the same quadratic. But for this expression, we'll just maintain one single variable, which is c over x minus 4. Let's look at an example of such an expression. So we are having this question now. So we look at the denominator. So for the x minus 2, it's non-repeated. This is a quadratic. It has the exponent of 2. So x squared plus 7. There is no factorization we can do further from here. We can't reduce this expression. And since we can't reduce the expression, it will take the form, our decomposition so will be of the form, we'll have a, since this is non-repeated, we'll have a over x minus 2 plus. So since this is a quadratic that is irreducible and it's non-repeated, so we'll have bx plus c over the same quadratic expression, which is x squared plus 7. So by doing so, this is the decomposition it will take. All we need to do here is now find the value of a, b, and c. So multiply the whole expression by the least common denominator, that is x minus 2 and x squared plus 7. So if we multiply that throughout this expression, we'll end up having 3x plus 16 is equal to a multiplying x squared plus 7, and then b x plus c multiplying x minus 2. Doing the multiplication, where we expand and we collect like terms, your final expression should look like this. You have a plus b with x squared plus negative 2b plus c x, and then plus, I'll write it down here, plus 7 a minus 2c. So that is after you expand this expression and also expand this one, and you collect the terms with x squared, you put them together, the terms with x and the constants. So when you reach this stage, remember what we've been doing. By using the definition of the equality of polynomial theorem, we're going to equate the coefficients. So here we can imagine that there is a 0 x squared plus, such that our coefficient here is a plus b, our coefficient for the x squared is 0. So we're going to equate by saying 0 is equal to a plus b. Here our coefficient for x is 3. Our coefficient for x here is negative 2b plus c. And finally, for the constant, we have 16, which is equal to 7a minus 2c. And then we can now solve the expressions we have. Okay, so solving our expressions, we can get the first expression and equate a to b. So this will give us a is equal to negative b. Now that we have the value of a, we can replace it in this expression. So that will give us 16 is equal to negative 7b minus 2c. We've replaced where there is a with negative b. And then we can also get the other expression, which is 3 is equal to negative 2b plus c. We can multiply this expression by 2 so that at least we equate with this the other expression. So that would be 16 is equal to negative 7b minus 2c. Then here we'll have 6 is equal to negative 4b plus 2c. We can subtract the two expressions. So we can add the two expressions so that we have 22 is equal to negative 11b. Then this is 0. So this gives us b is equal to negative 2. So if b is equal to negative 2, remember we said a is equal to negative b. If we replace here with negative 2, we'll have a positive 2. So our a is equal to positive 2. And if we replace the value of a in this expression, we'll have c will be equal to negative 1. So now that we have these expressions, we can write them in our partial decomposition. So that will be, so our final expression now will look like this. So it will have 2 over x minus 2 plus, so our b is negative 2. So we'll have negative 2x minus 1, which is c, over x squared plus 7. And we are done. So the last case is where we have a repeated quadratic factor. So if you look at the expression given, x minus 2 is not repeated, But the other expression is a quadratic. We have an exponent of 2. And then this quadratic is repeated. So we'll apply the concept of repeated linear factor and also for a quadratic that is irreducible, because we can't reduce x squared plus 4. There is no simpler method to reduce it. So the partial decomposition of such an expression will take the form, we'll have a over x minus 2 since it is just a linear factor, plus, so remember how we're reducing for a repeated factor first. So this is now a quadratic, so the two concepts will come to play. So that is, we can write it in this form, a1 x plus b1, then this is over x squared plus 4. So we've taken the concept of a quadratic factor that is irreducible. So we've used a1x plus b1. And since it is repeated, we'll have another expression again. So this will now be, we can say a2 x and then plus b2 plus b2 over, we'll have now the repeated factor, which is x squared plus 4, then we square it. So that's how we can do the partial decomposition of such an expression. Let's look at an example. So in this example, we have this expression. So if you look at the denominator, first it's a quadratic and it's irreducible. We can't reduce this quadratic. Then it is also repeated. So for this one, the partial decomposition will be of the form. There's no space here, so let me just write the decomposition from here. So we'll have ax plus b over the first expression, which is x squared plus x plus 1. Then since it's repeated, we also have another expression, which will be cx plus d over now the repeated factor, like that. So that's how we're going to reduce it. So since it's repeated, we have to repeat with the exponent of 2 now. And from here, having these two expressions, we're going to multiply them with the lowest common denominator. So we're going to multiply the whole expression with this denominator. So if we multiply with this denominator, what we're going to have, the numerator will maintain. So we'll have 4 So if we've multiplied throughout the expression with this denominator, we're going to have the first part ax plus b multiplying x squared plus x plus 1, so which is this part. Then for this one, it will just be the way it is, which is cx plus d, because the two would divide. This part and that part would divide. So from here we can expand and then we collect the like terms. So our expansion, if you expand this part and you collect like terms, the values with x squared, x cubic and the like, we're going to have an expression of the form so our expansion and the simplification will finally look like this, which is a x cubic plus so due to space, let me just write the other expression down here. So this is the final expression you're going to have. So you need to expand, you multiply ax by x squared, it will give you x cubic. So just like that, you expand, then you collect terms, so with the variables that you're having. So those with x cubic, you keep it separate. Those with x squared, you also put them together, and those with x and the constants. So when you get here, we equate like terms of the coefficients. So for x raised to cubic, the coefficient here is a, the coefficient here is 4. So our first value will be a is equal to 4, or 4 is equal to a. Okay, let me write it that way, since that's what we've been doing. So we have 4 is equal to a. And then the coefficient here is a plus b, the coefficient here is 5. So we have 5 is equal to a plus b. And then the coefficient here is a plus b plus c. Here the coefficient is 7. So we have 7 is equal to a plus b plus c. And finally, the coefficient here is, the constant here is b plus d, and here it's negative 1. So we have negative 1 is equal to b plus d. From here, we can solve the systems of equation. First of all, we already have a is equal to 4. So if we replace 4 here, we make it cross the equal sign. So b will be equal to negative 1. Is it negative 1? No, just b will just be equal to 1. Since if this is 4, 5 minus 4 is just 1. So then we have the value for b. So if we have the value of a and b, that is, there is 4 here, 4 plus 1, that is 5. 5 crossing the equal sign, we have 7 minus 5, that's 2. So we have c is equal to 2. And finally d, if we replace b with 1, negative 1 minus 1, that is negative 2. So d will be equal to negative 2. So these are our values, and we can replace them in our expression. That is, so we're going to replace our values that we had. So we had ax plus b. So our a, we've said it's 4. So we'll have 4x. Then our b is 1. So 4x plus 1 over the expression, which is x squared plus x plus 1. Since my space is not enough, I'll write plus, but I'll write the expression here. Plus we had, is it cx plus d? So our c is 2. So we'll have 2x. Our d is negative 2. So we'll have negative 2 over x squared plus x plus 1. But this time, this is a square. And you're done. So those 4 cases are what's major guidelines when solving an expression of partial fraction. So the last part that I would maybe give an example on is an expression where our numerator has a higher exponent than our denominator. So for all the questions we've been looking at, the exponent of the numerator has been smaller than that of the denominator. So if you look at this expression from solving, it had x raised to 3. This one is x raised to 2, but due to it has this square, if we were to expand this expression, our exponent on the denominator will be x raised to 4. So it's higher. So for each and every example we've looked at, if I can just take you back, this one also we had the numerator was having a lower exponent than the denominator. So before you solve any partial expression, make sure the numerator has a lower exponent than the denominator. Now what happens if you meet an expression or question where it's opposite? The denominator has a lower exponent than the numerator. So for this example, where we have the exponent of the numerator is 3, the exponent of the denominator is 2. So the numerator has a higher exponent than the denominator. So we need to first make it into a proper fraction. It's improper in this case. So we're going to do the polynomial long division. So that this will reduce the exponent of the numerator. So doing our polynomial division, we start. So x squared into x raised to 3. We're going to have x multiplied by x squared, we have x raised to 3. And then x multiplied by negative 7x, will have negative 7x squared. Then we subtract. So negative 4x plus x squared, will have 3x squared. Then dividing here, x squared into 3x squared, will have plus 3. Then 3 by x squared, we'll have 3x squared minus 3 by negative 7, so we'll have negative 21x. So if we reduce this one, if we drop this one, we'll have 19x. Subtracting these two expressions, we'll have negative 19 plus 21x. That is we'll have 2x. So now this is reduced with our remainder 2x minus 35. So now dividing this into this, we've gotten x plus 3 with this as the remainder. So our expression is now of this. It's now of this term where we've divided, so we have x plus 3, then this is plus 2x minus 35, which is our remainder, over the denominator that we had was x squared minus 7x. Okay, so first of all, when you get an expression of the numerator has a high exponent, you do the long division. The answer that you get and the remainder, you will put them in this format. This is the answer and this is the remainder. So the remainder will be divided by what you had as your denominator. So now we'll work on these two, on this part, while maintaining our given solution. So now we're going to find the partial decomposition of this expression here. So if we look at the denominator, okay, let's take the expression. So the expression is this, over x squared minus 7x. So below here, this is a quadratic. But is it reducible? The answer is yes. So we can reduce this quadratic into, we can factor out x. So we'll have x, then we'll have x minus 7. So it's reducible to that format. And this becomes a linear factor. So now we can find the partial decomposition of this. That is, so we'll have a over x plus b over x minus 7. So now if we multiply the whole expression by this denominator, our solution will be 2x minus 35 is equal to a x minus 7 plus bx. If we expand the term and we collect like terms, we'll have an expression of this format that will be a plus b x plus negative 7a. Here we can equate the coefficients. The coefficient of x here is 2. So we have 2 is equal to, and the coefficient of x here is a plus b. The constant here is negative 35. The constant here is negative 7a. So here if we divide through by negative 7, our value for a will be positive 5. And if we replace 5 where there is a here, we'll have 5 crossing the equal sign will be 2 minus 5, that is negative 3. So b is equal to negative 3. So we can replace this in our final solution. So our final solution, we need to write the original expression, which was this. So let's write the expression. Okay, so this was our expression. So the decomposition, we'll first write the solution that we had for the long division. So when we divided, we got x plus 3. Now the partial decomposition, where we've gotten our values of 5 and negative 3. So our a is 5. So 5 over x plus negative 3 over x minus 7. So this is what you do for an expression where the numerator has a higher exponent than the denominator. So thank you guys for watching. See you in the next tutorial.